Hi, my name is Rolf Agner, and welcome to On Air with SICK. In this season of our podcast, we're providing insights from experts in the world of autonomous mobile robots, or AMRs, in the manufacturing and material handling industries. Today on our show, I'm joined by Stefan Nusser, who is the Chief Product Officer at Fetch Robotics. He oversees product strategy for all Fetch robots and solutions. Stefan will be discussing the differences between the various types of mobile robots, how Fetch utilizes RFID technology for process improvements, and also how Fetch Robotics is helping during this global pandemic. This interview will be two parts, so join us next time to hear the second half of our interview with Stefan. I hope you enjoy our conversation. I looked at your blog, and you talk about AGVs and the differences between AMRs. Could you speak to that a little further and explain the differences?
An AGV uses some kind of guidance, essentially, and that guidance is created by modifying the workspace. Right, so you explicitly put in it's almost like getting sort of railroad track put in place, right? And you can do that either by having magnetic strip in the floor. You can do that by having visual locators in certain locations that help the AGV find out where it is. And that means that the deployment process requires planning. And that means the deployment process takes long. Right, because you're touching, you're modifying the environment, a new environment, and you're setting it up for the AGV ahead of time, or you're modifying an existing environment. But because of the fact that you're making these modifications, you have to sit down, you have to think through where you want the AGV to be able to do. You have to make the modifications, and then you can get the AGV to run. So there's two components here. One is the actual the fact that you have to make these modifications, and then there is also the fact that the requirement to be thinking ahead and to be planning doesn't really allow you to be adaptive and kind of iterative in how you deploy. Right. So there's two factors at play here. Right. You sort of looking at a set of tasks that are going to take months. Because of that, you are going to be more static in how you define those routes. Right, the AMR essentially learns the environment, and I say that in quote. It's not actually machine learning. It's a more rigorous, more predictable process than that. But the AMR, when you put it in a new environment, you essentially show it around. Right, you take the robot, you show it the entire environment, and while you show it around, it will create a map. And from that moment on, the AMR is able to localize itself on that map. Right, so once you have the map, you can then go in and say, okay, there's a couple of locations of interest here. I want you to go from location A and location to location B. And then the AMR is good to go, right? So it's a task that takes hours, right? Maybe a day or two to get that up and running. And that's nice because they're easier to deploy, but it's also nice because it allows you to be starting small, to be iterative, to be adaptive. And that really is what kind of, for me, is the more game-changing thing is when people deploy AMRs, they are more. It is really more like getting a cloud service, right? You don't need a lot of infrastructure. You get a little bit of functionality. You do some testing, a pilot, and then if you like what you see, you gradually scale up, and you can use AMRs in the same way, right? So those are the two facets that I think about. It's not a long process to be deploying an AMR, and therefore you can be more adaptive, more iterative in how you create and then evolve your footprint of automation.
You get a lot of flexibility. I've been working with AGVs going back to the late 1970s, when things were very, very primitive. And people had to cut out concrete in the floor, lay in wires. It all had to be planned, as you said, over and over again. And you had to have a fixed idea of what you wanted to do. And if you had to make a modification, which I've seen many customers have to do later on, it requires digging into the concrete, whatever it was. If you're using that kind of a method, travel by wire, travel by maybe movable magnetic targets, maybe it's a little easier. There has been progress, and as you mentioned, perhaps having some type of visible target to have a navigation type system follow. Even back in those primitive days, there were obstacles they had to overcome, varying loads on even an AGV. It changed how the vehicle performed. and you had to do a lot of calculation on maximum load, minimum load, decel turning because the vehicle behaved differently. There was sliding and friction and not sliding and loaded and unloaded and stopping speeds. Now, do AMRs do anything for considering this type of thing and as far as it being adaptive for this type of situation?
Yes, they do. They definitely do. So some of these challenges, some of these needs are the same for the AMR, but it travels differently when it's empty from when it's loaded. The traction is different when the AMR is on sort of a more slippery type of ground, as opposed to it being on sort of a good rough, slightly rough, but not too rough surface. So these are all considerations that exist on the AMR as well. The AMR in general is a little more sensorized. If you want software capabilities that are similar to a modern workstation. So those are capabilities that AMR companies like us are constantly refining, refreshing, updating, right? So AMRs, they're dealing with exactly the same set of requirements. They are getting better and better at doing that. The more we sort of have them out in the field and the more we get feedback and the more we see how they behave.
Okay. Very similar to a little experience that I had back in the 80s when I was working a lot with motors and drives and servos on vehicles this and other things. Previous to that, when people sized a motor, they had to go through all kinds of guessing on what was going on and a lot of calculations, very cumbersome. Change any variable, oh boy, back to the drawing board. In fact, getting back to the early 80s, it was done by slide rule for the most part. There were no computers available. Perhaps you had a calculator, and that would speed things up. But then we moved into the late 80s. Personal computing came on board, and I remember working with computer programs. I don't know if you've been around long enough to remember Lotus 123 spreadsheet.
I do remember Lotus 123.
But
I grew up in IBM.
I was able to use motor data, motor curves into a very extensive spreadsheet. And it was so easy then to just pop in a new variable, different inertia. Somebody wants to start up faster, slow down more, carry a heavier load, and the program would tell exactly how much current, how many amps, how many volts was necessary to do this job. And then you could properly size a drive. And it just changed the whole industry so much. I can see AMRs being very, very similar to this.
Yes, and they are, right? And that's a space where a lot of advancement has happened over the last, I want to say 10 years, 20 years. There's control system at every level. You compare the state that you think the robot should be in, the state that you think the motor torque should be in with sort of the actual state. And if you see it deviating, then you can draw conclusions from that. It's like maybe there is some slippage, right? You're turning faster than you would have expected, right? So those control loops happen at many levels in these AMRs. And again, they make them adaptive, right? It is easier. I think the general trends are more sensors, more sensorization, and many more of these control loops at all levels, right? Where we monitor what's going on, where we take corrective action, right? And that allows, like really that is the trend that has given rise to the AMR or one of the trends is sensor technologies, right? And with sensors, you get data, and with data, you get the ability to create models, to process the data as it comes in, to react to changes in what you're expecting to see, or to react to any kind of situation that you believe you can discover in the data that you're getting, right? So that is the trend that's been feeding the AMRs, and that's why today you can have a machine that sort of behaves differently depending on the kind of environment that it's in, and a machine that detects when there's a human around and it slows down. Like these are all things that we're doing thanks to sensor technology and our ability to interpret these sensors very quickly on the fly and then sort of choose what to do or react to the interpretation that we've made from the data. Like that I think is at the core of the advancement here.
You said the magic word for a company like SICK, sensors. Can you?
It wasn't on purpose. Right? No, it is a key ingredient here.
What type of technology, sensor technology, are you using to accomplish this? The navigation, the mapping, and this type of thing.
We use a laser scanner, also called a LiDAR. It is similar to the technology that you sometimes see in self-driving cars, but it is sort of a more compact version of that technology. It is essentially a rotating laser beam that gets reflected off surfaces and then travels back to the AMR where it gets timed. And then based on that timing, we can calculate the distance of the object that the laser beam has hit from the AMR, from the LiDAR scanner. right? So what you get from the LiDAR scanner is essentially a matrix, an occupancy grid that tells you where, relative to the LiDAR, there's obstacles in the space. Right? And that is how, when you first sort of let the AMR loose in your environment, you drive it around and the LiDAR keeps running and it measures the distance. And that is how it discovers the walls, the sort of any static structures in the environment, any shelves or racks that you may have, any tables. It sort of sees all that and creates a map. And then once you sort of drive around the workspace, it compares the current observation with the map. And that is essentially how it keeps itself localized. So it knows what direction you're heading. It gets the LiDAR reading, the distance measurements from the LiDAR, and therefore it can calculate where it is moving in the map that it has previously created. Right? So the laser scanner is sort of one of the key sensor technologies here that's been enabling the space on the market of AMRs. And if you look at AMRs across the board, not just ours, the entire market, many of them are using SICK LiDARs, and almost all AMRs that I know use laser scanners as the way to do mapping and localization.
Okay. For those listening, if you want to learn more about LiDAR technology, a good place to visit is the Aerospace Museum, the Smithsonian Institute in downtown Washington, D.C. You nodded your head, Stefan. Have you been there to the Time Museum?
No, I haven't, but it sounds like a great way to experience the technology.
There's a wing in that museum called the Time Museum. And in that Time Museum, when you walk in, they have one of the DARPA vehicles. And the DARPA vehicles was the contest. I don't know if they still have it, but they had it every year for autonomous vehicles and how to get from point A to point B the fastest. And they have this LiDAR technology on these vehicles. And then they have an explanation of it in that wing of the museum. Very fascinating for anyone who would like to learn more about it. What about vision? Are you using vision to do any of this also?
Yes, we do. We complement the LiDAR with 3D cameras. So the LiDAR is sort of a more sophisticated technology. To make it cost effective, most people use what's called a planar LiDAR. So it only really sees a slice of the world, a single slice that's parallel to the ground. So to understand what the LiDAR of the AMR is seeing, you need to know at what height it is mounted. Right, so our LiDARs are mounted for one of the models at about 12 inches off the floor. And so that is how the robot sees the world. It is a slice where it sees all the obstacles, all the walls, all the columns, all the racks. But it really only sees it in one plane that is 12 inches off the ground, parallel to the ground. For example, if I go with that example, the 12 inches off the ground, you may not see a set of forklift tines that's all the way at the bottom. It may be below. Or you may not see an overhang that's sticking out of a rack in a warehouse. It may be too high for the 12-inch plane to see, but it may still be low enough for the AMR to bump into it if it has, for example, a cart loaded and is moving it around. So we need to be able to see vertically also, and we do that with 3D cameras. Right? So 3D cameras are a less expensive way of seeing the three-dimensional structures, but they don't have the range. What we do is we combine a LiDAR with a 3D camera, and that gives you sort of a good distance vision, but it's planar. And then within a range of, let's say, 5 to 7 meters or 5 to 6 meters, you get 3D vision then, and that is what you do with the 3D cameras. So most AMRs I'm aware of have a combination of 1 or 2 LiDARs and a couple of 3D cameras.
Okay, do you marry that technology together, taking one in relation to the other to create a true picture of what's there?
Yeah, that's exactly how it happens. You fuse sensor fusion, right? You fuse sensor input from both of these sources, and then you create sort of a view of the space around the robot. And that is how we localize. That is how we discover and keep track of obstacles. These could be static obstacles. And when I say obstacle, I mean any object that is near the path of the robot. This could be moving obstacles, again, like a walking human. So these things register in the fused set of sensor data. I'll see it first in the LiDAR. As we get closer, I add the 3D information from the 3D camera, and that allows me to react and adjust my path accordingly, right? The path for the AMR, unlike the HEV, the AMR has the ability to adjust its path dynamically. So if it sees an obstacle, it knows where it wants to go. It sees an obstacle, and as it gets closer, and as the obstacle is not getting out of the way, the AMR decides to replan. right? And then he plans around the obstacle, and as long as it has enough safety cushion on the sides, it'll just navigate around the obstacle, and then it's going to be back on its path.
Well, that's all for today's episode of On Air with SICK. Thanks for listening, and thank you to Stefan Nusser for informing us of the differences between the types of mobile robots and how they can improve processes. Join us again next time for the second part of our interview with Stefan, where we'll discuss how to keep people safe around AMRs. If you ever want more information on anything we talk about in this podcast, send us an email at info@sick.com. Until next time, I'm Rolf Agner, and this has been On Air with SICK.